Welcome to Einstein's Mechanics. In this episode, we are going to solve two problems on the Thevenin's theorem. So, example, find the current in the 4 ohm resistor using Thevenin's theorem. So, we have our circuit and we have to find the current passing through this 4 ohm resistor. So, how do we do this using the Thevenin's approach? In the previous episode, we talked about how to do the Thevenins and the requirements. So straight away, we are going to solve this problem. We are interested in finding the Thevenin's voltage at the 4 ohm resistor, and we also find the Thevenin's resistance, and we will also find the load resistance. For the load resistance, it is given as 4 ohms. Are we okay? So let's try to find the RTH. So finding the Thevenin's resistance. We are to draw the circuit again, and here we are going to short circuit the voltage source and open circuit the current source, because when you look at the circuit, we have a voltage source and a current source. So we are going to apply what we already said. So this will be the diagram for finding the RTH. Starting from the current source, we are going to open circuit, meaning current is not going to flow through that direction. So we can assume this part is off because it is open, no current is flowing. So our analysis is going to start from this 5 ohm resistor, and we have this 5 ohm resistor too. This 4 ohm resistor is what we are considering. So here we are going to find, let's call this point A, B, and this is what we are interested in, our RTH. We still have another resistor up here, and this voltage source is short circuit. It is removed as if it does not exist. So this is our diagram. This is the 10 ohm, this is 5 ohms, and this is also 5 ohms. So here we are going to find the total resistance in the circuit, and that will be the Thevenin's resistance. So this, what do we say? It is very simple. We can see that if current is flowing through this part, the same current passing through the 5 ohm resistor is going to pass through this 5 ohm resistor, meaning they are in series. And this arrangement is going to be parallel to this 10 ohm resistor. So with that idea, let's find our total resistance. We can see that, let's call the total resistance R1 to be equal to 5 ohms plus the 5 ohm, and that is going to give us what? 10 ohms. Are we okay? So I can say that the RTH will be equal to our R1 being parallel to the 10 ohm resistor. That is going to be 10 ohms is parallel to 10 ohms. Are we okay? So when we have two resistors of the same value and we have to find the total resistance, if they are connected parallel, it is half of the value. So that is going to be 10 divided by 2, and that will be 5 ohms. Meaning our RTH, the Thevenin's resistance across the terminal AB is 5 ohms. So now we have two parameters. We have our load resistance from the question. We have our RTH calculated. It is left with our VTH. Let's look at how to find the VTH. So finding our VTH, the Thevenin's voltage across the load resistor. So here we are going to redraw the diagram again by considering all the current and voltage source, and also open circuit the load resistor. So this is what we are going to have. This current source is still there, and we have our resistor, the 5 ohms. This 4 ohms is going to be still there. and we have our 10 ohms, our voltage source. So here we have also our 5 ohm resistor, and this will be our circuit. So here we have 2 amperes. This is 5 ohms. This is 10 ohms. This is 20 volts. And let's pay attention here. This is going to be out, because we are going to find current across the 4 ohms. So meaning we are going to open the terminal as we did as. So here it will be for our VTH. Are we okay? So now let's look at this. If we are going to assign current, now this whole part forms loop 1, and let's call this loop 2. If this part is going to bring current through the circuit, we are going to get our current, say I. This current I is the same current flowing through this 5, because if we are to assume that it's going to split here, it is open, so no current is going to flow. So all the currents are now flowing through the 8 or the 5 ohm resistor. So no current through this part. And this current is still the I current. Now, when it gets to this junction, it is going to split. So this part, we already have it as 2 amperes, meaning if current I is coming and it's split into 2, one is 2 amperes, then the current across this 5 ohm resistor is going to be I minus 2. Is that right? Yes. So our current passing through this part will be I minus 2, because the I is splitting. By KCL, current leaving should be equal to current entering. So the current will be I minus 2. So we can find the I by considering this loop 1. Now we can see that the voltage source, which is 20, should be equal to the voltage drop across this 10 ohm, which is 10 by the current I, plus the voltage drop across the 5. And we know that this 5, as at this 5, the current is still I, so that will be 5I, plus the voltage drop across the second 5, which is 5 multiplying current I minus 2. And when you simplify this, you are going to get your 20I should be equal to 30. And this means that our I should be 3 on 2, and that is 1.5 amperes from the loop 1. So we are also going to use an idea here to find our VTH. Please pay attention and you will get it. If we are going to assume this as a loop, this part as a loop, then we can also make analysis that this 20 volts is equal to the voltage drop across the 10, which is 10 multiplying by the current I, plus the voltage drop across this part, which is our VTH, the voltage VTH. It also makes sense, right? Yes, because we are considering this part as a loop, and voltage at the VTH plus voltage at the 10 ohm is equal to the voltage also at the 20 volt. The same thing if you consider the whole part as a loop, it is also going to be true to help you find your current I. So here we have the value of current, so we put in the value and find our VTH to be equal to 20 minus 10 by 1.5, and this is going to give us 5 volts. So our VTH here is 5 volts, and we have our RTH also to be 5 ohms, and we have our load resistance to be 4 ohms. So we can find the current by combining these 3 parameters in series to each other to get the current passing through the 4 ohms resistor. Very simple. So let's try to combine them in series. This is going to be our diagram. So this will be our VTH and this will be our RTH in series with our load resistance, and we are good to go. So this is VTH, this is RTH, this is RL. So let's call the current passing through as I1, which is the same current passing through the load resistance, which is the 4 ohms, so that we answer the problem. So if this is true, then from the Ohm's law, we know I is equal to V on R. Therefore, our I1 is going to be VTH on the resistance, which is RTH is in series. So we'll add the total resistance. This is going to give us I1 should be equal to 5 on 5 plus 4. And our I is going to be equal to 0.555 amperes. Therefore, the current flowing through this 4 ohm resistor is the same current flowing through the RT. So our answer will be the current passing through the 4 ohm resistor is 0.555 amperes. Very simple. What you have to know is the way to find your VTH using either of the analysis or your RTH. Let's look at the second example here. So in this example, it says find the current in the 2 ohm resistor using Thevenin's theorem. So very simple and straightforward. We are going to find our RTH, we are going to find our VTH, and we have our RL to be. We are interested in the 2 ohm resistor. So now let's find the RTH. So finding our RTH, which is the Thevenin's resistance. So in this circuit, we have a voltage source, we have a current source. So we are going to short circuit the voltage, open circuit the current source. So this is what we are going to have for the diagram. Short circuit the voltage source means we take it out and we have our 6 ohm resistor. Open circuit means the 2 ohm or the 2 ampere current source is going to be out. It is going to be open, so no current is flowing. So it is the same as it is out from the circuit. So this is still the 6 ohm here, and we have our 4 ohm resistor also here, and we are interested in finding the RTH at the terminals of the 2 ohm resistor. So this is going to be our diagram. Let me call this part as AB, and we are looking for the RTH. This is 6 ohm and this is 6 ohm. This is our 4 ohm. So finding the RTH is very simple. So here we can see that the 6 ohms, the same current is going to pass through it. So they are in series. So I'll call their effect as R1, which is 6 plus 6, and that is going to give us what? 12 ohms. Now, this 12 ohms is going to be parallel to the 4 ohm resistor, and our RTH is going to be 12 multiplying. You can use the inverse formula and you can still get it, and that is going to be 12 plus 4. And with this, we are getting 3 ohms for the RTH. So now we are through with load resistor, we are through with RTH, we are to find the VTH, where you have to pay attention and listen. So here, I would prefer to use the nodal analysis approach to find my VTH. That will be very simple for me. You can use the branch, you can use the mesh, you can use any of the analysis to find. So now, using the nodal analysis, find for my VTH, the Thevenin voltage. I'll have to draw the diagram again so that we can see how current is being distributed. So I still have my diagram. So let me use the original diagram from the question so that will be very simple. We are interested in the 2 ohm. So this terminal is open. When you are finding the VTH, there is no short circuit of voltage or anything. So this is our VTH. So now let's start to distribute. We are going to use the nodal analysis, meaning I'm going to call here V1, I'm going to call here V2. Remember, all this part is grounded. You understand? You can check the previous episode to understand how the nodal analysis works. So I'm grounding this part. All this part is grounded. So V is equal to 0 here. I have my V1 and V2. So a current I will be moving through this part. So I'll call this I, and this current is going to also split here. I'll call this I1 or I2. In that way, this current is also going to pass this way as my I3. So the nodal analysis. Now, what do you see? We can write at node 1 where we have the V1. At node 1, we will write the KCL for that. That is going to be this current I plus the 2 amperes. They will be equal to the I2, right? Yes. So straight away from nodal analysis, please check out for the nodal analysis video to understand everything about it. One thing about the Thevenin's theorem is you have to get the circuit analysis approach in order to find your VTH. You have to either understand the mesh, the nodal, the branch, so that it will help you to find your VTH. So expressing this I and I2 in terms of voltage, then we are going to see that this current is moving from the 12 volts to V1. So that is going to give us from the 12 volts to V1, and it is passing through the 6 ohm resistor plus 2 is equal to I2 is also moving from V1 to V2 through the resistor 6 ohm. And when you make your analysis, well, this is going to give us 12 minus V1 plus 12 should be equal to V1 minus V2. And your simple equation is going to be 2V1 minus V2 should give you 24 as my equation 1. Simplify this part and you will get this equation. Now at node 2, at the second node, what do we also have at the second node? At the second node, you can see that the current I2 is coming from this side. And remember, this same current is going to pass through this part because if it is going to split, this part is opened, so there's no current going to flow. So our I2 current is the same current as what? I3. So now we write it in terms of voltage. I2 is from V1, and V1 to V2, everything is over the resistor, which is what? 6, and that is equal to I3. I3 is also moving from V2 to the ground, minus 0, through the 4 ohm. And with this, you can simplify this to get your simple equation. This implies that our equation is going to be 4V1 minus 10V2 should give me 0 as my equation 2. You can take your time and go through the analysis to get the equation. So this is also my equation 1. Now solving equation 2 and equation 1 simultaneously, you are going to get your value. Now, the value for the V1 is going to be 15 volts, and for V2 is also going to be 6 volts. So now let's look at something. Nodal analysis. This V2 means the voltage across the terminals. This part is 6 volts. And you know that this is parallel to the VTH. This V2 is parallel to the VTH. And what do we know about parallel voltages? They are equal. So we can say that V2, the voltage across these 4 ohms, which is measured as V2 and is 6 volts, is equal to, this is also what? Parallel VTH. VTH, and that is also equal to 6 volts. So our V2 is equal to VTH, which is 6 volts. So we can now draw the diagram for the VTH, the RTH, and the load resistor in series. Once you get to this point, you are through with your solution and you can move so easily. So let's draw the series arrangement and get the analysis. So this is going to be my VTH. This is going to be my RTH in series with the load resistor, and I am good to go. So this is my load, which is 2 ohms. This is my RTH, which is 3 ohms, and this is my VTH, which is also 6 volts. By the Ohm's law, I is equal to VTH, everything on RTH plus RL, and that is going to be 6 on 3 plus 2, and that is going to be 1.2 amperes. Therefore, the current passing through the 2 ohm resistor is 1.2. The same thing is happening in the big diagram. Are you okay? So Thevenin's approach is very simple, but it will be complicated at the VTH calculation if you are not good with the analysis using the branch or the nodal or the mesh current. Each of them, you should get to know them and apply any of them in finding your VTH. Thank you for watching this episode. More examples will come your way. Take your time, study, and subscribe to the channel. Thank you for watching this episode.